Hello, my name is Francesco Bronzino, and I'm an assistant professor at Università of Rome. Today, I will present to you the work that I've done in collaboration with my colleagues at ISI, Nokia Bell Labs, Princeton University, INRIA, and the University of Chicago on the design and development of Traffic Refinery, a system that enables the exploration across the costs and performance for network traffic representations for machine learning on network traffic. In the last few years, we observe an increasing use of machine learning to solve networking problems. This trend was initiated by the security community, who adopted machine learning-based solutions to tackle issues such as intrusion detection. Later on, classical problems of networking have been approached using machine learning, such as packet classification and quality inference. Lately, even routing issues have been modeled as machine learning problems. What we observe is that across all these problems, there is a common issue that arises when developing models, and in particular that model designers have to take a decision about how the traffic that is measured and collected in the network is presented to the models themselves to maximize their performance. Let's look more concretely what we mean by that. Here in the figure, you have the 5 classical steps of the machine learning pipeline, from data collection all the way to model testing. This pipeline, aside for a few details in the early phases, is not that different from the typical steps of the machine learning pipeline. In this work in particular, we focus on the first 3 phases because these are the most unique for networking. And in particular, how we go from traffic to the features that we present to the models. Let's look into the details of what it means. Here we have a graph representing our typical network with traffic flowing from 2 elements. What is normally done is that we're going to have a system that collects traffic and measures it, transforms it into some features or representations. Some examples of representations are the ones produced through aggregation and sampling, so aggregating some larger amount of traffic into a single statistic or sampling subset of traffic. A typical example of this is throughput, which is the most commonly available representation for model designers because it's the normal output of conventional measurement systems. Another type of representation is event detection. So basically, we want to detect events that happen as part of the ways that networks operate. For example, the connection establishment between a client and a server. Finally, we have seen a trend of new types of representations being presented by the community, like, for example, the one in the figure where some researchers looked at the problem of machine learning on traffic by noticing that machine learning models works very well for images, so they found ways to transform traffic into images by encoding it as scales of gray images and use that as an input to the models. What we observe in this work is that there are limitations if we solely rely on the traditional network representations that are made available by measurement systems, like the throughput one that I mentioned before. And in particular, we observe that if we solely rely on these features, we might be missing out on models that are a lot more performant. In the figure in particular, you see that for a model used to infer the video quality, if relying solely on the representations available through NetFlow, one of the standard representations for network traffic measurements, we might be missing out on all the blue shaded portion of the models where we have better performing ones that use different and more advanced features. The problem is that creating these features and exploring which of these features work best can be very problematic and challenging. This is because of 2 reasons. The first one is that collecting network traffic in such a way that enables the exploration can be very storage costly, can create big issues in terms of storage. Here we show an example of 2 types of data collection from network traffic. The first one is NetFlow, which I mentioned before, that only collects aggregated statistics. This does not generate, obviously, a large amount of data, but if we use some representation like pcaps that allow us to then derive new representations, the amount of storage necessary explodes very rapidly. Additionally, if we only rely on offline traces like pcaps, we are not able to estimate what is actually going to be the ultimate cost of collecting the representations that we are creating. To solve this issue, we created Traffic Refinery. Traffic Refinery has the goal of enabling model designers to explore which data representations are most effective by also providing ways to understand in a granular way what is the cost of collection for each feature. Traffic Refinery is built on three design choices and goals in particular, and I will be detailing each one of them right after. The first design property of Traffic Refinery is providing a way to flexibly and easily define new features for users. In particular, it does so by using a service-driven packet processing pipeline. A user doesn't have to do anything else than specify for which domains or IP address spaces wants to collect traffic and define which features for each of these subflows wants to collect. The system will pick up the configuration file where these details are specified and will start to automatically collect traffic for that specific category of services and applications. If the user sees that a feature that he wants to collect is missing, or he created a new feature, he can easily implement it using a number of abstractions that we provided to users to quickly write just two functions of Golang code and place these newly created functions in the structure of the file systems of the system, and the system will automatically collect information and start processing features for the services defining the configuration file. In parallel, while we developed Traffic Refinery to be as flexible as possible for end users to collect all possible features, obviously, we wanted to provide a way to also run this system at line rate, so up to 10 gigabit, and to provide ways for users to profile the cost of each features. And we did so by implementing the system to support fast processing using a flow cache that stores information of each flow that can be rapidly accessed, and support 10 gigabit per second packet processing, as well as provide profiling for three different metrics. The first one is the average amount of memory, so the amount of state required by each feature in isolation. Second, the amount of processing required by each feature in terms of the average processing time for each packet. And finally, the amount of storage that each feature is generated in terms of how much data has to be exported from the system to export the feature in consideration. The last characteristic of the system is that the system can run both on live links, so collecting traffic in real time, or to work on pre-recorded pickup traces that can be replayed on the system to recreate conditions that have been recorded from the outward. To evaluate the functionality of the system, we worked on two use cases. The first one, looking at a random forest machine learning problem to infer the quality of video streaming from encrypted traffic. The second one, looking at malware detection using a convolutional neural network technique, which employed the image-based representation that I mentioned before. We implemented both use cases and evaluated them both on pre-recorded traces as well as on a campus network. The first evaluation that we did was in how simple it was to extend the system to collect these the features required by these models, in particular features that were application specific. Happily, we realized that both use cases only required a minimum amount of lines of code to implement them. In particular, 100 lines of code for the first use case, 150 lines of code for the second use case. We will get more in detail now, discussing the first use case. So here we have the same representation that we had before about the representations creations in the context of network traffic. And for video streaming, this is very similar. We have our services on the left. Our service on the left, we can think of Netflix as an example of a service that is transmitting traffic to a client. We capture this traffic, we apply a number of transformations and create a number of features. From these features, we create the model and we test it and get some results. In this specific work, we use the models created in our previous work to categorize the features that can be possibly collected and used for this problem into 3 categories. The first category is the network layer features, which are the ones that are commonly available from measurement systems. Think of NetFlow that I mentioned before, so throughput, packet counts, and so on. The second category is transport layer features, which require keeping track of the state of the TCP connection, so the transport connection. And finally, the application layer ones. So features that are derived not by applying the packet inspection, but rather by looking at the patterns of the traffic that video streaming applications are generating. So we implemented the collection, the feature collection functions for this use case, and we only and we created the 100 lines of Go code necessary. We introduced it in the system and we ran the evaluation. The first thing that we observed is that for the inference models, in particular in this case, we are seeing the inference models for video, for resolution inference. We observed that, well, first of all, the model on the left, the one using only network features, is clearly the least performing one. And then we basically observe that there is a difference, there is a small difference in terms of accuracy, so performance, for the 2 models using either only network and application features, or the one using all the features. But while the model using all the features has a slight advantage in terms of performance compared to the other one, it comes at the cost of 2 orders of magnitude extra amount of memory necessary to collect these features, which means that we demonstrated practically that in terms of amount of memory, so state, the transport feature collection having a large impact, but a small benefit in terms of model performance. Similarly, we evaluated the other metrics. Storage followed the same trend as state, but inversely, for processing, we observed that there was not a clear difference between the processing time required for processing packets for the different groups of features. In particular, you can see here that, yes, there is like transport features are slightly more complex to calculate, but if we look more in detail, looking at the number of packets per second that are required to be processed to achieve given network speeds, if we select 10 gigabit as the goal that we define for our system, all the feature groups that we considered before can be processed in our system without being a bottleneck in the processing pipeline. Finally, we also evaluated the malware detection use case. And in the figure, you can see the trade-off between the average processing time of running the system and extracting from the system only the raw bits of the packets used as an input to the model versus using these versus transforming these bits into the image that I described before exporting out. And we compare the amount of processing time to the average per flow storage necessary. What can be observed from the figure is that even though the processing time of processing the image itself on the system is orders of magnitude more costly, it actually creates a lesser amount of output to be extracted from the system, suggesting that different deployment strategies can impact the decisions on which representation to use for the collection system. In particular, in this case, if a system is less processing constrained, but more storage constrained, might decide to actually process the images on the system itself. In conclusion, we presented today Traffic Refinery, which is a proof of concept system for joint exploration of cost and performance for machine learning networking models. We demonstrated that Traffic Refinery and its approach of exploring costs and performance of models at the same time can provide ways for system designers to take meaningful decisions on how to deploy and to build their models and systems. And moreover, that a fine-grained cost analysis can lead to different choices for traffic representations depending on the scenario. In the future, we aim to work with a broader range of costs, addition to the ones that we explored in this work. We want to better automatize the process of how this exploration can be performed, and also study what impact could hardware solutions for processing packets can have on the cost of the models. With this, I finish my talk. I thank you. I look forward to seeing you at Sigmetrics 2022. And if you want to look at the system, it's available on GitHub and it's fully open source. And feel free to reach out if you have any question.